Okay, good evening, everybody. So I'm so thankful that everyone is able to make it here tonight. We're all very interested in the research topic for today. I'd like to provide a bit of context about the Testing the Waters program that we facilitate throughout Haliburton County and how it will connect to the research that you'll be hearing about this evening. Testing the Waters has been a long-term community-based water quality monitoring program that's been delivered through our Woodlands and Waterways EcoWatch initiative since 2022. And so participating lake associations have been collecting standardized water quality samples each year, helping build a long-term baseline data set that allows us to better understand the health of our lakes and how they're changing over time. And so in 2022, when we launched this program, we always had this vision that it would be more than a water quality monitoring initiative. We wanted to be able to build a long-term monitoring network that could also support new research opportunities as they emerged. And so at the same time as when this program was established, we partnered with Trent University to begin collecting samples that could be used to study freshwater microplastics. And so that decision is what brought us all here today. Since then, we're very happy to say that this Testing the Waters program has grown to include 27 lake associations across Haliburton County region. And thanks to the continued support of Haliburton County, we've been able to expand that number of lakes and sampling locations over time. And so while the water quality program has continued to grow, the resources dedicated to this microplastic component have sort of remained static and focused on the original partnership that was established in 2022. And so as a result, Jacob's research is going to be based on the original long-term data set that started then, providing a unique opportunity to examine several years of consistently collected samples locally in Haliburton. I also want to take a moment to recognize that none of this would be possible without the incredible dedication of Lake Association volunteers. You know, every sample that we collect represents volunteers giving their time to this monitoring program. And the commitment not only helps us understand the condition of what our lakes are today, but also help create opportunities for research projects like the one we'll be hearing about this evening that are building upon those data sets. It's also a really good reminder that long-term monitoring programs like this one, they don't happen just by happen chance or by accident. And they're really reliant on sustained partnerships and ongoing support. So as you represent yourselves as lake residents and lake association members and continuing to work with your municipalities, I would certainly encourage you to keep emphasizing the value of long-term water quality monitoring, the importance of maintaining it as a community priority, because it's through opportunities like this and continued investment in programs like this one where we're able to benefit from not just monitoring efforts today, but again, looking at opportunities for future research and better equipping you guys with informed decision making for lake management. So tonight, we're very fortunate to have Jacob Wyonch from Trent University with us to share the results of this work. And without further ado, I'll pass it over to you, Jacob.
Thank you, Frank. So yeah, welcome. I've done one or two presentations like this before, but this time, yeah, we have a full 4-year data set, and maybe we can even start to talk about some ways to try and fix the problem of microplastics in our lake. So it is going to be a bit of a longer presentation, so I have a quick little timeline. We'll start by talking a bit about microplastics in general and how they've become such a problem. And then we can take a quick glance at the monitoring program. But I also want to talk about the limitations in microplastic research, just some big ones. And then that'll lead us into hopefully a cool and interesting live demonstration. And then it'll be a whole lot of results. Like I said, 4 years of data, but I'm hoping I've sort of put it into enough space that everyone can digest it. And then, yeah, we'll have a discussion about what solutions may look like, and then we'll conclude by turning it back to the monitoring program and sort of looking into the future. So, let's start with one of the biggest questions we ask when we look at microplastics. Where did they come from? Well, first, we have to understand our definitions. So in our case, microplastics are just pieces of plastic under 5 millimeters in length, and they can come in a variety of shapes and colors, so long as that particle has the same chemical structure of plastic. So maybe this fragment up in the top left came from a takeout container. Maybe the fragment on the top right came from a rope. Maybe the foam down there came from a car tire, and maybe this fiber came from a polyester shirt. It would also be handy to know that all the particles pictured here did come from our own lakes in Haliburton. I picked them out myself. So, we already know plastic pollution is a global problem, and we know many water bodies around the world suffer, but we don't exactly see litter dumped on the shoreline of, say, Halls Lake, which I have a picture of on the left there. Yet there were microplastics in Halls Lake. I found them in the spring, in the autumn, and in fact, I found microplastics in every one of the lakes we sampled, in every season in all 4 years. So, off the bat, if you learn one thing about microplastics today, I want it to be that they are some of the most persistent pollutants I think we have ever manufactured. And it really is unimaginable to think that such a sort of human material like plastic can be found in some of the most pristine water bodies we have in the world. But it starts to make sense once we kind of dive into how they behave. So I want to take a person who's wearing a normal polyester shirt, and they happen to just throw their water bottle, which is made from polyethylene terephthalate, into the garbage. And so the person goes home and they put their polyester shirt in the dryer after they wash it. And then that plastic water bottle finds its way into a landfill. So in that dryer, as the clothes create friction through that mechanical spinning, large swaths of fibers, microfibers, can shed from those polyester shirts, and they're just thin enough to slip through the dryer filter out into our atmosphere. And then in the landfill, the ultraviolet radiation from the sun can begin to weaken that plastic bottle. And then the physical stressors from maybe being crushed or plucked around by wildlife can cause small fragments to chip off that bottle. And so let's say a large rain event occurs. The polyester fiber, which could have been traveling hundreds of kilometers by now through the air, is intercepted by a raindrop and it lands in a river. The rain can also saturate the soil around the landfill, and that water starts to run off the surface, the ground surface, into the river as well. The fragment can be picked up in this runoff, and it can also land in the river. And then, as both these particles are ground and crushed by debris and sediment flowing through the river with them, the fragment specifically may begin to shed hundreds of particles from its surface, each one being a fraction of the original fragment's size. The particles can also develop these very intricate cracks and crevices on their surfaces, and they start to become sort of a sponge for maybe other pollutants that are also in the water. And very interestingly, they can actually be a favorable habitat for microscopic bacteria and even viruses. And so eventually those particles will flow downstream and possibly into one of our lakes and remain there. They can float through the water column in that lake. They can be ingested by aquatic life, or maybe they can settle into the sediment and be pretty much entombed for possibly years to come. Now, I want you to take this little story and imagine it happening to millions of pieces of plastic every day. And that's sort of how we begin to understand why microplastics are such a problem. And so that's basically why we monitor. We know even the plastic we don't throw out, the plastic we wear on our bodies, they can still pollute our lakes. The problem of microplastic pollution is simply unavoidable at this point, but we can measure it, we can monitor it, and then maybe even in the future limit it. So our current monitoring program has fully analyzed 4 years of surface water samples for microplastics. We've taken them in the spring and autumn from 18 lakes, as Frank said, around the Haliburton County. But what exactly is the end goal here? What do we actually want to know about microplastics? So you can imagine with a problem as new as microplastics, research a decade ago had relatively simple objectives, such as this paper here from 2013. They were simply just sampling the surface waters of the Great Lakes, and they were measuring the occurrence of microplastics, whether they were there or not. But these days, when we monitor, we can ask much more complex questions and conduct a thorough, intricate analysis, but at the end of the day, we're still just looking for the occurrence of microplastics. See this paper from 2026, this year here, they pretty much did the same thing. They sampled water and they looked for the occurrence of microplastics. So, this research is essentially really slow and it's very strenuous. Um, we are still having a pretty hard time asking the basic questions of, why are there microplastics here or there, and how did they get there? So, let's start with what this monitoring program can't do. So we aren't exactly going to find out if these microplastics are hurting us. In fact, the experts don't even know those answers. Um, but what we can do with this monitoring program is begin to be proactive. We can learn how microplastics find their way through the environment around our lakes, and how they get into those lakes, and how sort of those trends and pathways might change over time. And, while we don't exactly know those very intricate and complicated health effects, I think a consensus from all of us would be that they're probably not good for us, obviously. So if we gather a bunch of this data now, we will know when and how to act in the future as some of that information on the health effects side begins to come to more light. So the slow process of microplastic research, it starts to sort of make a bit more sense when we look at just a couple of these pictures. So to the left is a picture of a filter paper, and these are actually where we put those microplastic particles from the lake water onto, and we look at these filter papers under a microscope. And from the picture, you can actually see how dirty they get. But then to the right, I've just thrown in some miscellaneous figures from usually from our final data. So, how do we go from looking at practically a pile of dirt to measured microplastic particles and very detailed characteristics on them? So, I don't think a lot of us are too interested in learning about data processing or statistics. So instead, I want to show something a bit more interesting. It's a small but very informative test that we use to find microplastics in dirty samples. So I'm going to stop sharing for a second here, and I'm going to switch my camera over to my little portable microscope here. So hopefully I'm kind of maximized on everyone's camera there. But basically what I have here is I've collected some actual microplastics. So we can see I have a bit of a lineup of them. And so normally these would be, yes, in a pretty dirty filter paper, surrounded by debris. And before I get to the hot needle, I just want to maybe take a quick look at some of these, and we can really start to see that surface, that kind of cracked and porous surface I mentioned earlier. So I'm going to zoom in real close here, and I'm going to try and focus. Um, and so, yeah, when you really zoom in on these particles, you can see they look kind of dirty, cracked, and old, and that's those pores and those cracks in the surface. Um, Let me just make some fine adjustments here so I can show you guys. There we go. So yeah, we have a little film here. It's polyethylene, so this is probably just a little plastic bag, and you can see how dirty it's gotten, how it's able to just kind of be a sponge for any sort of other particles. And then we have a little rubber polyethylene kind of foam-like object here. And it's kind of shining there. You can really see just how sort of detailed and how much more there is even on the microscopic scale. We have a little chip of paint here, And yeah, it starts to something that is very apparent is they really start to change color too as they degrade. Sorry, I'm trying to work this just from the camera as well. So yeah, we have some polypropylene, kind of a fiber bundle coming from a rope here. And so yeah, these surfaces get very, they can get very intricate, even just from this scale here. If we were able to zoom in any further, it would start to get pretty interesting looking. But I want to show you guys this hot needle test. So what we do here is when we find a particle, uh, we basically take a picture of it on our regular microscope. The microscope I have in the laboratory is a bit more high definition, so those pictures come out a bit better. But we take a picture of it and then we have that in its you know, original size and kind of shape we found it in. But then what we do is we actually have a soldering needle we take, and I'm gonna kind of put it there, and that's the tip of it. And basically what I'm doing right now is I've turned this needle on and I'm heating it to 350 degrees Celsius. And so the theory behind this hot needle test is that microplastics, because of their chemical structure, their melting point is actually much lower than organic debris we find and maybe little pieces of sediment. So you can touch a lot of that debris on the filter paper with a very hot needle like this, and it won't really react like a microplastic will. What a microplastic will do is it will very clearly melt. You'll lose mass on it. And so it's very distinct, even when you're looking at it under a microscope to see. And that is sort of how we're able to actually find those particles in some of the mess of the filter paper. So I'm gonna demonstrate it right here. I'm gonna zoom out so I have a bit more room to work with, and then I'll refocus. So let's start on this. I'm only gonna do a couple of them because some of them are a bit too small. They might be hard to see. But we can start with this rope here. I'm going to get in as close as I can, like that. There we go. And I'm just going to poke at the end of it there with the needle, and we'll try and see just how it works there. So I'm gonna, yeah, shaky hands. Usually we eat before this. So yeah, you can see it practically disappears, and it really kind of gets freaky. Yeah, it's like there'll be some color changes, but yeah, right there, it kind of turns into almost like a goo. And yeah, that's that much lower boiling point, or melting point, yeah, where it practically melts. And so I have another big particle somewhere here. Yeah, right here. This is polyethylene again, but this is a garbage bag here. And you can just maybe touch a point there. And yeah, it really just melts very clearly. So, oh, yeah, just a tiny little bit of smoke there as well. So yeah, we do that on a bunch of particles through this mess of debris, and sometimes we even go further and kind of try to look at particles that stand out from the background in really messy samples because you don't want to spend all day just poking at every little bit on the filter paper. But this kind of white fiber bundle I have here is, I believe it's cotton. And so we're going to see what happens when I poke this because it is not a plastic. And I believe it's cotton. This is my first time poking it though. So, uh, yeah, see? So I'm pretty sure that little piece there was stuck on the tip of my needle from the other plastics, but you can see I can really mess around with it. And the only thing that's really happening there is that there's some changes in the color, and that's basically the oxidation. So it's kind of burning and crisping, but it's not exactly melting. So yeah, I'll poke a few more here just for fun, because yeah, some of these particles they melt pretty weirdly. Um, I think this is more cotton, maybe. Yeah. Or no, there it is. It's kind of melting. Sorry, I did get these particles from a shoreline cleanup, just some extra particles from another study. So These aren't exactly, this is a styrofoam right here, and it really will just melt up and disappear on you. Um, but yeah, essentially that's it. It's a very handy test. It's very accessible too. You know, you don't need $1 million piece of equipment to conduct it. But then while we're on the microscope here, I also want to show you guys kind of, you know, the size and how that works because we think of, oh, under 5 millimeters, but it's a bit more deeper than that. So I've lined up some stuff here. So first I have sort of another piece of that garbage bag here. And so this is 1 centimeter in length. Sorry, it's a bit flipped, those labels. But yeah, this is 1 centimeter. So this is quite big. And on our filter paper, we'd be like easily able to see this. It would be taking up like a quarter of the filter paper there. So this is well over 5 millimeters. Therefore, we wouldn't actually count this as a microplastic. And then we have this sort of little film here, and this is 1.5 millimeters. So this is still quite big. I'm not fully zoomed in on my microscope here, so around all the way down to about 1 millimeter when you're on the microscope. These are very easy to make out, and this would be a very easy hot needle test to conduct. But then we move down to zero point 0.5 millimeters or 500 microns. And so below zero point 0.5 millimeters is actually where we see majority of our plastic. And so it starts to get pretty small here. I have to zoom in pretty significantly to get a good look at this particle. And you can really start to see that while the needle test is great, it can get quite difficult here because this is very small and I'm trying to touch this with the tip of a needle that oftentimes is bigger than the particle. And I'm trying not to melt that whole particle because I do want to reserve it for further analysis. So that's 500 microns, but we can go even further here. I'm gonna have to focus to find it. But yeah, right here I have some uh, micro beads that we keep in the lab for quality control. But these are about 100 microns, so zero point 0.1 millimeters. Finicky microscope, sorry. So yeah, these start to get very, very small. And this is where I'll end off just with this kind of scale of reference. But I'm going to slowly kind of zoom out, trying to keep it focused on that particle, just so you can see um, pretty much, yeah, how small they get. So we're still zooming out, we're still zooming out, we're still zooming out, and you can finally actually see the label above it. And so, yeah, um, basically, these particles are usually most frequently very, very small, and they can be a real pain to deal with. But yeah, I hope that was pretty interesting. I mean, when do you get to see the actual contaminant with your own eyes? I'm going to switch back to my face here, and then I'm going to come back to the presentation. Mm, I don't know what happened there. Okay. And so we'll be moving on now with some results. So I'll be showing you the microplastic concentration from each of our little sampling campaigns. And then we'll be moving on to looking at the shapes of microplastics we're finding, also from each campaign. And then maybe one of the most important parts is we'll be looking at the types of microplastics we're going to find. And so by type, I sort of mean, polypropylene, polyethylene, and then we'll be looking at those from each campaign. And then we're going to go into a bit of some more complex analysis I've done. It's a bit harder to explain, but I do think it's still important to talk about. So, let's jump right into our first sampling period, which was in the spring of 2022. And we're looking at our kind of key indicator, microplastic concentration. So when you see MP per MP slash L up there, that's basically the amount of microplastic particles we're finding in 1 liter on average. So off the bat, what were the highest concentrations? Well, we can see majority of the lakes well under 5 microplastics per liter. And the only lakes of huge note here were Stocking, Potash, and Winona Lake, and they were hovering much closer or even above 5 microplastics per liter. But when we go into the autumn of 2022, surprisingly, all those lakes that were over 5 microplastics per liter were now amongst the lower concentrations. And Stocking Lake still remained close to around 5 microplastics per liter, but Spruce Lake actually had the highest concentration in this period. And we also see lakes with close to no microplastics in that spring period, such as Mesquabi, Oblong, and Little Kinesis Lake. They're now starting to approach that 5 microplastic per liter mark. And then in the spring of 2023, it was a rather unique period. We actually saw the highest single lake concentration in the whole study period, and that was at the top there from Big Hawk Lake, and it had a kind of rather astonishing concentration of almost 15 microplastics per liter. Meanwhile, we had Drag, Haliburton, and Little Hawk Lake also had their concentrations sort of moving towards that 5 microplastic per liter mark. And then in the autumn of 2023, there's kind of yet another drastic change. We actually found no microplastics in the Big Hawk Lake sample. Not to say that there were no microplastics in the lake at that time, obviously, but in our sample that we took specifically. And there was also a decrease in microplastics from those surprising lakes in the spring. Instead, we now see sort of those noticeable increases in lakes like Mesquabi, Negaunee, and Cedar Lake. So we're kind of all over the place so far. And then in the spring of 2024, there was once again, it was a rather unique period where instead we actually saw our lowest average concentration across all the lakes. The only lakes to almost reach 5 microplastics per liter were Stocking and Winona Lake, who have sort of started to develop a trend of bouncing back and forth between almost no microplastics and up to this 5 microplastic per liter mark. And then meanwhile, the remaining lakes were rather low and you know, mostly across the board, even those ones that we have seen some fluctuation from in previous periods. And then in autumn 2024, there was actually a general increase across almost all our lakes, but it was only very marginal. Oblong Lake was the closest to around 5 microplastics per liter, but most lakes were sitting at concentrations that were sort of in line with their historic average. And then in spring 2025, we saw yet another unique event. So Big Hawk, Stocking, and Drag Lake all had concentrations that seemed to just bounce right up to almost 10 microplastics per liter. And then meanwhile, the next highest concentration came from Paddy's Bay, actually, up on Big Kinesis Lake. But it was still well below that 5 microplastic per liter mark. And so the rest of these lakes, and they had noticeably low concentrations instead, almost across the board in this case. And then our final period in autumn 2025, we can see that those three lakes that kind of ballooned in the period before, they have lowered quite significantly. And instead, the two noticeable lakes here were Spruce and Little Hawk Lake, who had both went from close to 0 microplastics per liter in that last period up to that 5 microplastic per liter mark. And then the rest of the lakes seem to hover around their historic averages. So, this is a pretty big picture here. So I'll give everyone a couple seconds if they want to take some last glances at it. But I will be giving some key takeaways from this. And so we can see the timeline seems to be rather just random. Concentrations are always surprising us, it seems. They're being both low, high, sometimes almost low to the point where we're not seeing any plastic. And these are some surprises. the first kind of big thing to me was the fact that season was not a strong indicator of concentration. I had expected a much larger concentration in the surface water in autumn because we're basically sampling following that summer period with all that activity usually directly on the lakes. But that didn't seem to really be expressed that clearly in the data. And then there were some sort of expected nuances. We did have big and small lakes, all with sort of the same average concentration. And this is actually due to sort of a dilution effect we see. So large lakes can take in much more microplastics because of their volume and because usually there's more activity on them. But since they have that larger volume of water, when microplastics have more space to disperse, that concentration that we measure, how many are in a liter, becomes sort of equal with those smaller lakes. And so overall, the sort of key hypothesis I had would be a significant change throughout the different seasons, and I thought it would have a pretty big effect, but it does not seem to paint a clear picture. But we can dive a lot deeper. So here now, I'm showing microplastic shape by percentage, and once again, we're going over each individual sampling period. And so something that's noticeable is that we don't really have to go into sort of a step-by-step walk through this figure, as we actually do see quite a clear trend here. It is fiber-shaped microplastics, so microfibers that are dominating the microplastic pools in these lakes. And that's followed by fragment shapes. And then I have the category of other shapes. So this would be films, foams, and microbeads, stuff that generally just wasn't that prevalent on its own, and they had to be grouped together. But we do see a couple of anomalies here. See, in spring 2024, other shapes did sort of have their most noticeably higher percentage of the pool. And then fragments actually ended up surpassing fibers percentage-wise in the spring of 2025. And so we can also look at this figure or these shapes just by individual lake here. And we can see that once again, across the lakes individually, we see that fibers are usually taking up about 50% of the microplastics we find in them. And we can also see some separate anomalies here. So in Drag Lake, we have fragments actually almost dominating the pool of microplastics rather than fibers. And then in Mesquabi Lake, other shapes actually, while they didn't dominate, they were noticeably higher than all of the other lakes. And so we can summarize the shapes here. The main takeaway is the huge presence of fibers, which we can actually understand pretty easily. So these fibers most likely originate from our polyester clothing, and I would say specifically bathing suits. They're often worn directly in the lakes, and fibers can easily shed off these clothes, as we know from our little story, and enter the lakes directly. But we can take what we know and think about some other things. So in spring 2025, it was the microplastic pool was dominated by those fragment shapes. It also correlated to the period in which Big Hawk, Stalking, and Drag Lake had significant increases in concentration. So that means those lakes received sort of a rather unique little dose of microplastics that period that were unlike what we were seeing on average over all the other periods. And then Drag Lake had a high percentage of fragments overall, and that was from the influx maybe of fragments in that spring 2025 period that influenced it. But maybe it also has a sustained presence of fragment-shaped microplastics, sort of higher than the other lakes we've been seeing. And then in Mesquabi Lake, there were many other shapes. So once again, films, foams, microbeads. And in spring 2024, other shapes had the highest percentage, but Mesquabi Lake's concentration was quite low in spring 2024. So we can kind of maybe deduce that Mesquabi Lake may be a bit unique in sustaining sort of a large pool of other types of microplastics over the entire study period, maybe not just concentrated into one period. Um, more unique pool of shapes compared to our other lakes. And then there is still more to know, though. So here's a percentage of plastic type. So we can read this graph as each color representing a polymer type or plastic type. Sorry, I'm very used to calling them polymers. So just clarification, that just means the plastic type. And we can read this graph as each color representing that polymer type. And basically, the bigger the colors bar, the more prevalent they are in each year of the study. So the first thing we can see is once again that dominating purple bar there, and that represents polyethylene terephthalate. And a very important distinction here to make is while we do call it PET, polyethylene terephthalate, we actually group polyester in with that plastic type because the chemical structure can be very similar. So when you look at that big, long, kind of complicated word, that basically means polyester. And so this graph basically helps us even more with our hypothesis. The fibers which dominate our study we now can see they are polyester fibers. So they're most definitely from our clothing. That was almost the last confirmation we needed. And the percentages of most polymers, they're staying relatively consistent throughout the years. And that means that our microplastic inputs, they don't really change significantly in terms of the types of plastics that are going into the lake. And we can look at all sorts of other polymers here. There's not a ton of them, which is good. Um, but we see polypropylene, we see polyethylene, polyamide, which is synonymous with nylon, and then we see paint. So we'll actually be sort of talking about where we might find these fibers very soon in the presentation. But we can also see the plastic type or the polymers by season. And so this graph can sort of be read like the previous one. You basically trace the bar to its season, and that bigger that bar is, the more prevalent they are. And so very interestingly, once again, the polyester presence is very prevalent in both autumn and spring. And that's kind of strange because we expect to see a high prevalence of polyester in autumn because we're sampling following that summer of a lot of activity on the lakes. But it's also there in the spring, which is following a winter of no activities. And so there, in general, doesn't really seem to be any difference in which plastic types we find between each season. And that kind of starts to raise even more questions. But the key takeaway is obviously we have our main culprit here. It's polyester clothing. Its fibers seem to contribute the most to the microplastic pool across every lake and across the entire study period. And the remaining polymers are not very diverse, which is actually a good thing. This means that there are only a handful of sort of large activities and sources that produce those microplastics into these lakes. So it's actually some pretty good news for any management down the line. And thankfully, as you'll see, many of these sources may actually be almost directly identifiable besides those polyester fibers from clothing. And yes, we will see that shortly. But we're going to sort of pivot here, and we have to consider that microplastics aren't the only sort of particles or things in our lakes. So activities around the lakes are connected to microplastics, yes, but they also exert different kinds of changes, such as changes in water chemistry. So far, we've only looked at just the microplastics. We haven't really considered the huge amount of variation these lakes have. Some of these lakes are much smaller, some are bigger. And in terms of water chemistry, it's always changing. And so it's kind of handy to realize that every time we do visit and sample these lakes, we're not really sampling the same water as we did the last time. So let's try to dissect microplastics in the whole picture. And so this graph is very abstract, but I don't want you to try to understand it. All I want you to focus on are the two different colored kind of circles there. So the red group on the right, they are lakes that have sort of a different kind of water chemistry status. They have a higher water clarity, so more clear water. They have higher dissolved oxygen, higher chlorine conductivity, and total nitrogen. And then the blue group on the left instead sees higher pH, higher total phosphorus, and water temperature. So we took these groups and we used a very complex statistical model that I do not need to talk about, but basically it lets us separate all the variation and influence that may be caused by water chemistry. And we're basically disentangling our microplastic data from just the messy influence of different source of different variables from water chemistry, land use, the lake profile. We're basically trying to just pull microplastic data out of that and look at it on its own. And it actually starts to look quite different once we do that compared to just those averages we were looking at earlier. And so here are the results. So we actually found that the red cluster lakes, which were characterized by, once again, that higher water clarity, dissolved oxygen, chlorine, conductivity, nitrogen, they consistently seem to show higher microplastics throughout the years overall. And there does seem to be an association here where as those chemistry variables increase according to our model, the microplastic concentration almost seems to follow in that increase. And so um, unfortunately, that's kind of all I can leave it at in terms of that complex analysis. It takes a lot of time. I'm actually still kind of grappling with these results right now. I kind of just found this out a couple days ago in terms of these last complex results right here. But yeah, I want you to know, you know, the full picture is mostly complete, 99% complete. But there's still some little things to explore that may actually lead to some exciting new results. I'm hopefully I'll be able to share when everything's said and done. Um, Hopefully that doesn't take much longer. But we'll pivot now, and I'm sure everyone's a little bit sick of numbers by now, so we can actually start to talk about maybe some solutions. So the first step in making some solutions is being aware. So let's start to become a bit more aware of the plastic in our cottages. And so I actually went down to a buddy's cottage a couple weeks ago. He's on Lake Kashega-Wigamog, or Kashega-Wigamog Lake, and I took some pictures with his permission of just around outside his cottage down by the lake. And so first we have the fire pit and we have the classic Muskoka chairs. I'm sure a lot of people have these. And usually they're a bit more affordable in their plastic version. And that's actually made from high density polyethylene, or you can just call it polyethylene. And then down at the dock, there's a variety of plastic. We have our boat covers for the weather. They're commonly made from polyacrylic, or more commonly polyester, our main culprit. And then we have many boats are obviously painted, not all of them, but many. And paint can contain kind of a wide variety of plastics as sort of ingredients. So we typically just say, paint is a polymer or type of microplastic. And then we have those buoys. I'm 99% sure we use them, to protect the boat against crashing up on the dock there. So those are commonly made from polyvinyl chloride. And then finally, we have our mooring ropes, and those can be made from a variety of plastic, such as nylon, polyester, and polypropylene. And it's very interesting because if we think back to the types of plastic we found in the microplastic pool, we found polyester most prevalently, polypropylene kind of second most prevalently, and then polyamide or nylon was in there as well. So if we're thinking about other sources, these ropes, they interact with the water. While they are built for the water, that water will slowly degrade them. So they may be also a significant source alongside that polyester clothing there. And then obviously a lot of convenient outdoor storage is going to be plastic. So similar to the Muskoka chairs, this box right here is made from high density polyethylene. And there were some inflatables stored in this box, and we would use those for tubing, lounging on the lake. So they're commonly made from polyvinyl chloride as well. Polyvinyl chloride may be better known as PVC, too, to put that out there. but those inflatables can also be polyurethane or polyester. And sort of kind of I caught those in the picture there. A pair of flip-flops on the left. I think they're a common sight though. We will very often leave our shoes hanging around on the dock at the cottage. But that comfortable kind of foam you're used to on those flip-flops is actually ethylene vinyl acetate, a type of plastic. And then I sort of have a bonus here. Many may be familiar with this. It's an exposed polystyrene dock float. And so I don't know all the details, but I do believe that these have been regulated very heavily now. And everyone just look at this picture. So we remember how plastic degrades. So the state of these floats, you can see the cuts and the crevices. This indicates that they have probably released, hundreds or thousands of polystyrene microplastics into the lake in the past. And so the ones in the picture here, they're not being used. But regulations did not really ban their use outright, but the purchasing of new polystyrene floats without an outer casing, I believe. So that means that, that these may still exist within some lakes. However, it is important to note that we did not really see a lot of polystyrene in our plastic types earlier. And then I think the last picture I have here, yeah, is stuff we bring to the cottage. So we have the infamous bathing suit here. So bathing suits are so commonly 100% nylon or 100% polyester. More commonly in our Haliburton lakes, probably polyester, as we can see. And then we have our fishing gear here. I'm not sure how many fishers there are, but there's a lot of plastic accessories with fishing. We have that soft plastic bait, which is made from plastisol, and it's kind of like a solution, but the main ingredient in there is once again polyvinyl chloride, PVC for short. Um, and then we have sort of hard plastic baits. Some of them can be plastic, and sometimes they're made with a bit of a unique plastic type, some more dense plastic type, such as this one, which is acrylonitrile butadiene styrene, ABS for short. And then we also have our monofilament fishing line, which is usually made from nylon, aka polyamide. So, we do see a signal of nylon from our lakes, albeit small, but it could be coming from those mooring ropes or maybe more prevalently that fishing line. And then, so how do we limit all these plastics, all these plastic items? The simplest solution is to replace them with non-plastic items. The alternatives do exist, but unfortunately, I actually can't really sit here and ask that of you. Non-plastic alternatives are usually A, extremely expensive, or B, extremely inaccessible, and C, oftentimes they're unreliable. They won't last as long as your plastic products. They may break down, need more maintenance. That leads to spending more money on them. And so, especially in today's world, we don't have the time, we don't have the resources to truly explore these alternatives because plastic has become such a central, convenient item in everyone's life. And so, how can buying alternatives be a very widely applicable solution when almost, every plastic item we've seen here can be easily bought at your local retailer? Meanwhile, these alternatives are usually expensive. You're usually shipping them from some very small website that is shipping from across the world. And so, simply put, I encourage anyone who's interested in alternatives to explore, and I would love to help, but I can't sit here and directly ask you to basically pay to fix the problem of the microplastic pollution. Because, in essence, you would be paying for a problem you didn't even start. So in that case, what's another alternative? We can maybe start to explore some non-plastic behaviors, I would call them instead. So once again, I have a picture here. And I think a possible behavior that may be applicable to a lot of people, maybe everyone, is rethinking our kind of short-term storage behaviors at the cottage. So pictured here are some paddle boats, and I looked at them and they had these big plastic hulls. And so they're sitting there on the lawn in the middle of the summer. and they're being stored against these rocks, day and night. They're being used frequently on the water, obviously, so we're going to keep them close, keep them convenient. The problem is they're going to stay here or they're going to get out on the water all summer and they're going to be sitting there through blazing heat and heavy rainfall. We've seen both this summer, right? So let's look back all the way to the start where we were talking about how microplastics degrade. So UV radiation and physical impact. We can start to imagine that these boats are baking in the sun, and that sun is weakening those plastic hulls. And then when a large rainfall occurs, or when they're put out on the water and they're being driven around, perhaps thousands of microplastics can be chipping off these hulls, either directly in the water or through rainfall, where they very conveniently, specifically in this picture, but I'm sure this is sort of a common look, they very conveniently wash down the lawn there straight into the lake. So maybe one kind of big thing to take away, I'm sure it can be applicable to a lot of people here, is to try and think about getting on top of, short-term storage. It is rather annoying to have to haul, especially those large plastic items back and forth from shelter during peak activities in the summer. But like I said, alternatives. Are usually expensive and inaccessible. This is a solution that I believe should be quite accessible and maybe widely applicable. And then the next thing is for the anglers out there, or maybe more importantly, the aspiring anglers. So one of the most important things about fishing is obviously knowing the environment you're casting into. Not only will it help you catch more fish, obviously, but it may limit your microplastic pollution. So when lures get caught in weeds and rocks, I'm sure anyone who's fished has been there before. Oftentimes it can be a bit of a struggle, but if it's, stuck there for good, you're forced to cut that line, and sometimes you'll be leaving a hefty, soft plastic, hard plastic lure and some fishing line directly in the lake. And we can be aware of different lures that actually minimize your loss in the weeds and rocks. So next time you cast, consider the lures pictured here. They're designed to basically avoid tangling up in weeds, bounce off rocks, so you're not getting stuck and have to cut. But any seasoned angler here will know these lures well, I'm sure. But it may be applicable to people starting to fish at their cottage, just getting into it very casual, like I fished for the first time at a cottage. So, people who do it casually don't know a lot about it. It's good to be aware of these things. And also, if you notice the kids are getting into fishing more, it can be a very important thing to teach them early on, uh, as, they may not be as aware of these microplastic problems as us. And so that was rather a short list of solutions, right? Well, it actually makes sense because, remember how slow microplastic research in general was taking us in the first place? So yeah, researchers are so frequently left with as many questions as all of you. These questions just require more and more time to study, and it ends up just making real accessible solutions, maybe a ways away. And trust me, I'm as frustrated as all of you with this. And yeah, sometimes, tackling a new problem like this can be very upsetting. But actually, I hope everyone here knows that they've already been helping solve the problem of microplastics in these lakes all the way since 2022, actually. Yes. So this monitoring program is actually sitting on the forefront of microplastic research globally. Your dedication to helping me analyze this many lakes simultaneously, as well as this many lakes over the long period of 4 years, actually helps in answering questions researchers all around the world are asking to this day about microplastics. So, every volunteer's time and every cottager's awareness of this problem is genuinely, priceless. You're kind of joining us as researchers as we navigate through this very sort of dark and confusing and messy world of microplastic pollution. So I want you to be proud of yourselves, and I also want you to be excited because, we're going to try to evolve this monitoring program to a scale that may be unprecedented in global microplastic research. Uh, you know, research is often, looking at little lakes, answering very specific questions. Not a lot of people are monitoring, so we really are on the forefront here. You and I, um, looking at these lakes over such a large period, and then after a while, after more hard work, maybe that list of solutions we've explored will become much longer. And so I'm going to conclude here. Another huge thanks to the cottagers, the volunteers, the associations. I think the level of support and awareness I see regarding these lakes is amazing. I don't think it's very common in today's world. So it does give me a lot of hope for solving problems such as microplastics. I encourage everyone to tune in on August 19th. We're going to be doing another presentation though it's at 10:30 in the morning there. It's going to be at Minden Hills, but it also is Zoom accessible. And I'm going to try and take a much deeper dive into what the future of the monitoring program holds. It may be a little bit more technical, but I encourage if you can make it on Zoom, make it in person, because I'm hoping, it'll be very exciting. And so thank you for listening to me for a pretty long time now. If we have time, I'd love to go over any questions, discussions. It's too long to talk about everything, so I'm happy to answer any questions people may have.
Yeah. So thank you very much, Jacob. We have one question in the chat from Jim Prince. So I'll read that one out and give you a stage to answer that. So most cottagers manage their own water filtration and treatment. Do cottage systems with 5 micron ceramic filters remove the majority of microplastics from their drinking water?
5 micron ceramic filters. So I would say, um, in this case, from the data we've gathered here, yes. 5 microns is extremely small, so that's going to trap any plastic we found in this study. But there are some caveats here. So, when we're looking at microplastics through a microscope, sorry, I don't want to go on too long because I could talk forever about this, but when we're looking at them through a microscope, even with that microscope, it gets to a point where they're too small for us to see. So, in essence, we're actually not capturing all the microplastics that may be in these samples right now. Um, and it's sort of a sneak peek at what I'm going to talk about more maybe on the 19th. But part of what we're doing over at Trent, part of my PhD, is actually trying to unlock methods to look at those smaller microplastics. So while I can say all the microplastics data you've seen today would sort of be captured in those very small filters, there's always the chance that microplastics as small as under 5 microns can be caught. But hopefully, unfortunately, we'll have to wait until the future. But I'm really hoping we can go back to more samples and actually try and look at microplastics down to maybe even that size as small as 1 micron, before we start getting into nanoplastics.
Okay, excellent. The next question is from Ron Parkinson. How is this affecting fish and wildlife?
Yes, so unfortunately, when I do talk about health effects, and how sort of early we are, how much we don't know. It applies to us and it applies to fish as well. Basically, it's very hard to establish any sort of solid health effects to actually tell you right now, but there is some sort of hope. It kind of ties back into those small microplastic issues. So we know that if fish obviously ingest enough plastic, larger plastics, it can lead to irritation, it can lead to inflammation, as it can with us as well. Microplastics have been linked to reproductive issues in a lot of fish, um, and sort of problems in fish, maybe a couple generations after those who have ingested a lot of microplastics. But when we look at the concentrations here today, these are generally have not been associated with any adverse health effects, any noticeable health effects, the concentrations in our lakes currently from this data. However, unfortunately, the whole picture is really just not answered until we might be able to get a good method and look at those smaller microplastics. I think to be specific, actually, um, the microplastics in this study, they basically go down to 100 microns or zero point 0.1 millimeters, similar to what you saw in the live demo, those little beads. Those were about as small as we can consistently capture. So especially with those health effects. While there isn't anything super solid in the literature right now, a lot of times those health effects are focused on that smaller range because smaller microplastics can get deeper in your body. But for now, it's if I had to say, if someone asked me, should I be worried or not, I would say no, you shouldn't be very worried right now. The concentrations we see have not been linked to any problems, and while we don't have the whole picture, oftentimes those health effects that have been studied in labs they actually don't really translate well to the concentrations we see in the environment. So oftentimes you'll hear about these really freaky health effects that have been discovered, but you have to sort of read into them because oftentimes they're kind of using a study setup that's not directly applicable to the environment. So there's a lot of caveats, but you know, one word answer, no. You don't have to really you don't have to you don't have to worry about the fish. And then in terms of what it's actually doing to them right now, probably not a lot, but it's very hard to tell currently, even for scientists.
Okay, excellent. And the last one in the chat is, do you have any thoughts on the degradation of materials made by recycled plastics? And are you able to pick up a distinction of these materials compared to others at either a macro or micro level?
So yeah, my thoughts on it are yes, they will degrade. Obviously improperly disposed plastic, that is subject to all the elements. That's the plastic that's going to degrade. Um, and then we have, items that are constantly interacting with the elements at our cottage that are degrading. And I think, recycled plastics, they sort of just morph in, with those in terms of like, maybe recycled plastic bottle. If it's something that you're using frequently, I do highly encourage it. But unfortunately, as long as it's plastic of any kind, its continued use will result in, microplastics being produced from it, albeit, if we're talking about an item you're using often that you're not, just about to throw out, then it'll be a much lower amount of microplastics coming from it. Single use, like a bottle that's kind of single use but has been made from recycled microplastics or recycled plastic, it's gonna pretty much behave the same. And so, in terms of the surface kind of degradation, we we have sort of a middle ground instrument there at Trent University. We basically use an instrument, and it sort of helps us basically find the plastic type only. And sometimes that plastic type can actually come up as maybe a recycled item, like recycled PET, for example. In terms of looking at that surface up close, though, while I did have some pictures much earlier looking at those surfaces, we unfortunately don't have instruments at Trent that can actually look at those, that can actually sort of study what's on those surfaces, what's happening at sort of molecular level. There are many papers on it, though. As far as I know, recycled and kind of new plastic, they basically behave the same. They'll degrade the same in the environment. But at the end of the day, I obviously encourage everyone to use recycled plastic products. Kind of keep it with you as long as you can, because if it's not with you, it's most likely ending up in a landfill, um, being improperly disposed. So obviously, we want to keep our plastic products in that circular sort of recycle and reuse loop we have.
Okay, excellent. And then just the last question in the chat. So, not sure of the presence of zebra mussels in the lakes you investigated. Are you aware of any research of microplastics in water that has been impacted by zebra mussels? Um,
Yeah.
yeah.
So actually, zebra mussels are, I believe, often used in health effects research and microplastics. And so I kind of just want to give the whole spiel because when we're looking at kind of health effects in the natural environment, that is sort of where microplastic research can really start to drop off in its ability. It's right now, it's just so hard to actually establish the effects of microplastics in the natural environment because maybe some of you have heard of this before. There's no control. We can't really isolate what microplastics are doing because everything has microplastics in it. But interestingly, with zebrafish mussels, I believe they are used very frequently in health effects um, research. So I could actually tell you, I'm not a huge reader on the health effects side specifically, but there's a ton of different kind of associations they've made. Um, it can damage. It's an endocrine disruptor. It's a neurotoxin at some points. Um, I believe it can lead to cellular damage, especially in the mitochondria. But when we're thinking of all these kind of crazy health effects, you know, a microplastic that can enter a cell is going to be quite small. So oftentimes, in terms of trying to find that in a natural environment, it can be hard. And it's actually been a relatively recent problem that microplastic researchers are working through trying to find those small plastics in the first place. But I think the most kind of important thing to know about these health effect studies oftentimes are being done in a lab. They're simulating an environment, and you can never perfectly simulate, nature, the natural environment. It's too crazy at every scale. And oftentimes they can miss the mark pretty heavily on actually trying to mimic it in laboratory studies. Second, they're using usually one type of microplastic. I think the most popular type of microplastic to use are these polyethylene microbeads. And so these beads, you're really not going to find them that much in a lot of different environments across the globe. So they're finding these health effects on one specific type of microplastic. Meanwhile, microplastics of a whole other shape, a whole other plastic type could actually differ quite enormously in their health effects. And then finally, the most important part is they are pumping these fish, these mussels, any sort of fish or aquatic life they use in these laboratory studies. Oftentimes, they are pumping them full of microplastics. They're using these concentrations that almost nobody sees in the natural environment. So it's kind of hard to connect it to what natural monitoring data sees, because we're not seeing thousands and thousands of microplastics per liter. And we're also not seeing all thousands of those being these polyethylene microbeads. So while there is a range of health effects, I think that's like, the most I can say with the health effects. It's just such a confusing time. We're getting better, obviously, but I always am disappointed in myself when people ask me questions about health effects because, that's what we want to know. But unfortunately, like I kind of touched upon, this monitoring program, we at the Trent Lab don't look at health effects. Other people do. Other people are doing amazing research on it, though. It's just simply too early for me to be able to tell you whether those microplastics are for sure affecting your wildlife, affecting you while you're at the cottage.
Okay, excellent. Well, I think that wraps up all of our questions for this evening. Jacob has his contact information on the screen there. If there's anything that comes to mind between now and 3:05 a.m. tonight, I'm sure Jacob would be happy to get some inquiries to his inbox. Thank you again so much for your time and all this great information, Jacob. It really is a pleasure. And if anyone here is interested in learning more and seeing the follow up to this, and on Wednesday, August 19th at 10:30 a.m. in the Frank Welsh Room at the Minden Hills Cultural Center. We'll be there with some more information. So thank you very much, everybody. Have a great evening.
Oh, and Frank, sorry, yeah. Thank you, everyone. And yeah, thank you, Frank, for helping me with this presentation. I am going to put in a quick survey into the chat here, And I'll also drop my email for anyone who missed it on the slide there. Um, it's a very short survey. I just want to kind of gauge how people interacted with the presentation. So it would be a big help if you could just take a minute or two and fill it out. But yeah, thank you everyone for listening. It's been a pleasure.